Okay, good morning everyone, welcome back. So last time we talked about how the congestion in transmission network affects the price, especially the nodal price. So that's why we have two different concepts, system marginal price, SMP, versus locational marginal price, LMP, or nodal price. So yeah, we have this terminology, nodal price. And today we keep talking about this concept, and actually we need to use the same diagram again and again, and you need to do your homework again to understand it completely. And so last homework I think you need to use linear programming, right? So you did that, and yeah, in the next homework you also need to solve the linear programming. So when you did your homework, you have a variable, the injection here, there, and there. So I think you have 2 or 3 variables, how much to inject at each node, and also that need to satisfy the maximum line capacity of each line, and also the total supply is equal to total demand. And so those things are the constraints, and you need to pick up the combination of P1, P2, P3 that minimizes the total cost. Okay, so that's the objective function. So this was the result right away. So you are familiar with this diagram, right? But I think we need to do this again. So let me draw the diagram here. So the reason why I'm doing this here is to help you do your homework. Okay. So we have generator A, generator B, and generator C, generator D, and the load here. This is connected. This is connected. So 300 megawatt is 60 megawatt. 50 megawatt impedance 0.2, 0.2, 0.1. So bus 1, 2, 3, and the maximum capacity is 126, 250, and 130, and the marginal cost is B6 and C14, D10. Okay. So yeah, you need to determine how much to generate. And so did you compute the nodal price of bus 1, bus 2, bus 3 or not? You didn't do that yet. So today we are going to do that, okay? So the nodal price is denoted by pi 1, pi 2, pi 3, okay? And the meaning of nodal price is that the meaning of nodal price is cost of supplying an additional megawatt hour of load without violating the security constraints. So if you increase the load here by 1 megawatt, how much we have additional cost? Okay, so that load need to be satisfied either from here or there or from here. But satisfying the security constraint, and we want to find a combination that minimizes the total cost. Okay, so we will compute pi 2 here, pi 3 here, and pi 1 here, nodal price. So, yeah, nodal price, locational marginal price, LMP, again, by contrast, the concept of SMP, here we have a single marginal cost, okay? But in this case, we have different marginal cost per bus. And the interesting part is that the nodal price of a specific bus is determined from generators in other buses. Can be determined by other generators in other buses. Okay? You see what I'm saying? Yeah. So, yeah, let's look at nodal prices. For the first case, node 1. And this one. Oh, I didn't. Yeah, so the generation 50 megawatt, 285 megawatt, and 0 megawatt, D 75 megawatt. Is it the same to the solution you already obtained? Same, right? So the nodal price of bus 1 is that when you increase the load here by 1 megawatt, actually the unit energy, what you can do. So this is the current power flow. And we see that this line is, the constraint is binding. Okay? But this line and that line, the maximum capacity is larger than that one. So when the load is increased by 1 megawatt, what you can do is, what can you do? How can you supply that additional megawatt in the most cheapest way? There are 4 generators, A, B, C, D. The marginal cost here. So this is the cheapest one, but its current generation is 285. So where is the maximum generation? Thank you. Where? Oh, that one. Oh, that's the capacity. Okay. So and 85. Okay, then we have all the information. So when the load here is increased by 1 megawatt, you cannot increase B because it is already at its maximum. But 50, 140, so you can increase this one. This is the second cheapest one. Okay, so the nodal price of bus 1 is determined by this generator, the marginal cost of this generator. So pi 1 is equal to the marginal cost of generator A, and that is $7.5 per megawatt hour. Okay, pi 1. So pi 1. And let's go to node 3 here. When the load here is increased by 1 megawatt, what you can do. So A, D. A, D, this is the price. A is cheaper than D, but in this case, you cannot increase the power of A because then it flows like that and flows like that, and this is already at its maximum. Okay, so even if A is cheaper than D, you cannot increase the power of A. So the next option is either use C or D, but D is cheaper than C and also at the same bus, so we don't need to worry about the congestion. So the nodal price of bus 3 is determined by generator D. So pi 3 is equal to marginal cost of D, that is $10. So this is yeah, $10. Okay, easy things, but let's think about node 2. When you increase load by 1 megawatt here, you may think I can increase the generation of C, but this is the most expensive one. So rather than increasing the power of generator C, you can think of using either A or D, because they are not at their maximum yet. But increasing the power here will violate the maximum power flow constraint here. So decrease this and increase that. There can be a solution, right? So yeah, let's do that. So to do that, we want to use the superposition principle. So again, when 1 megawatt is injected, because the impedance is 0.2, 0.2, 0.1, it is splitted 0.4 and 0.6. And similarly, when 1 megawatt injected here, impedance is 0.1, 0.2, 0.2. So yeah, 80% and 20%, right? So the amount of injected here is denoted by delta 1, delta P1. Okay? And the amount of injected power at about 3 is delta P3. Okay? So this delta P1 plus delta P3 should be equal to delta P2, and that is 1 megawatt. So when the load is increased by 1 megawatt, how much we need to inject here and there. Okay? And also, this delta F12 is the increased power flow on this line, but that should be 0 because it is already, the constraint is binding now. Okay? So this one, delta P1 plus delta P3 should be one equation. And so 0.6 delta P1 plus 0.2 delta P3 should be 0. Right? So yeah, two equations, two variables, and solutions. The solution is that one. So decrease 0.5 megawatt and increase 1.5 megawatt. So from this, you can compute the nodal price of bus 2 this way. How much does it cost to supply 1 megawatt hour for node 2? So increase 1.5, the generator D here. So yeah, marginal cost of that, decrease 0.5, and the marginal cost of that. And that is 11.25. Okay. So yeah, this is also easy one. So now pi 2, 11.25. Okay. By the way, chapter 5 is very long. And you start to solve linear programming. You need to solve linear programming again. And finally, we will go to power flow equation and optimal power flow. There is non-convex problem. Okay. And we will consider later the losses in the transmission line as well. So congestion and power losses. Okay. So here are several interesting observations. Generator A and D. Generator A and D are marginal generators for bus 2 because A and D determines the nodal price of bus 2. Okay, in that sense, they are the marginal generators. Okay, and generator B and C are not marginal because they do not determine any nodal prices in this network. Okay, so when you think about unconstrained system, that means the line capacity is infinite and no losses. That means all the generators and loads are connected in a single bus that is same to that condition. In that case, so zero constraints, that means we have a one marginal generator. Do you see what I'm saying? The system marginal price, SMP, is determined by the most expensive generator. Okay? So the most expensive generator is called marginal generator. Okay? So when there is no constraint, infinite capacity, all the generators and loads are connected in a single bus, we have one marginal generator. Even if we have several generators, the most expensive one determines the SMP. But we have M binding constraints. M binding constraints means that M transmission lines are at its maximum power flow limit, right? In that case, there are M plus 1 marginal generators. Okay, so yeah, 0, 1, M plus 1. Assuming there are at least M plus 1 generators, yeah. When there are M binding constraints, we have M plus 1 marginal generators. We will visit this later. Okay, so prices at nodes. So prices at node where there is no marginal generator, for example, node 2, the price is set by a linear combination of the prices at other nodes. Here, node 1 and node 3. Okay? Agree? You look skeptical. Yeah, skeptical means, how can I say? Skeptical means I'm not quite sure, I cannot believe, something like that.
I believe.
Okay. So, yeah. So when you study English, you can use Ch5, of course you know that. And I introduced deepl.com to some of you. This is very similar to Ch5, and it has two parts, translator or writes. So when you write English here, it is translated or, okay, translator and write. If you select write, when you type some English sentences here, then it is revised automatically. Okay, and so when you write a paper, why don't you use it? You don't have reason not to use it, but you should be able to select the correct one. Okay, the fact check is up to you. And another one is Collins Co-Build English Dictionary. Is there anyone who knows it? Is there anyone who knows it? No? So this dictionary is unique in the sense that it explains the word using sentence. Okay, so skeptical. Where is it? It looks like just other dictionaries. Not easily persuaded or convinced, doubting, questioning. This is not what I'm looking for. Actually, why is it like this? Something has changed, but check it later. So typically, Collins Co-Build Dictionary explains the word using it in a sentence. Okay. Anyway. Yeah. So summary for 3-bus systems. Consumptions, productions are listed there, listed here, and we computed nodal price or nodal marginal price. That one, and so consumer payment is, so each bus generators are paid at the nodal price. Each bus consumers pay at the nodal price, right? So the total consumption times nodal price is the consumer's payment. Okay, this times that is that. And producer's revenue is nodal price times production is that, okay? So the total payment from customers and the total revenue of the producers are that. And as you see, they are different. And the difference is called what? Congestion surplus or merchandising surplus. This money is collected by the system operator. Okay, but yeah. So far, everything looks okay, but actually, we are talking about power system economics. Economics is economics. You know, goods are exchanges. Power system means we have a physical law. Power flows based on physical laws. So there are several counterintuitive observations. So let's see what that is. The first one is, okay, we already computed LMP here, 7.5, 11.25, 10, right? So, and so this power, where is it? So given generation that, you can determine the power flow on each line. So that is this one, that one, okay? So can you see something interesting here? What is interesting? What is interesting? What is interesting? Can you remember what happened when we connect two different countries, Bulgaria and Slovenia? The marginal cost here is very low. This is very high. And when they are connected, power flows from here to there. That's natural. But here, power flows from bus 2 to bus 3. Cheaper, more expensive. Why is it? Power flows from the more expensive bus to less expensive bus. Okay? Why is it? Because we are considering power system economics. Physical law governs that. Okay? Even though we are doing that by minimizing something, but anyway, we need to satisfy the physical law. So this kind of counterintuitive flows can happen. Okay. Then, under this circumstance, can you think of you are power producers, either A, B, C, or D, who can take the advantage of this kind of weird things? I mean, if you are power producers, yeah, you may want to, of course, you want to maximize your profit. So you want to exercise your market power somehow. Who can do that? Just guess. A, B, C, D. Well, it's not clear now, but somebody can do that, okay? Yeah, power flows from high price to low price. Counterintuitive flows. And so prices at nodes without a marginal generator, this one, can be higher or lower than prices at the other nodes. And yeah, in your homework, you will see this one. Nodal price sometimes can be negative. What does that mean? That means when you consume energy, you get paid. You consume energy and you get paid. Okay? Why is it? Because by doing that, you can contribute to make the system secure. The transmission line capacity, the limits are satisfied. Okay, so that's why you can get paid even if you consume some energy. So yeah, nodal price can be negative. Do your homework. And actually, yeah, predicting nodal prices requires calculations, including the optimization, linear programming, and so strategically placed generators can control prices, exercise market power. Okay, and network congestion helps generators exert market power. Exert means exercise market power. Okay. So let's do that together. Nodal prices and market power. Same situation, but suppose that originally the maximum capacity here is 130 megawatt, but this is reduced to 65 megawatt because of some maintenance. Okay, so and also this generator C is the most expensive one. The marginal cost is $14. So generate zero power. But this guy is desperate to produce, which means it has, even if the output power is zero, it needs to turn on the power generator and it generates some cost. So, but he doesn't want to turn it off because turning it off and turning it on incurs additional cost. Okay, so he is desperate to earn money and he decides to bid at a very low price. Okay, bids like that. So even though the marginal cost is this one, from system operator's perspective, yeah, their bidding is this much. And when the system operator computes the cost, they need to use this one. Minimize the total cost, assuming this marginal cost for this generator. Okay? So when these two things have changed, this one and the maximum flow limit, what happens? That's your homework. The solution is in the next slide, but you need to compute that. So when these two things have changed, okay, to do that, first what you need to do is, because the marginal cost of this generator is changes like that, first you need to solve economic dispatch. The total load is 300 plus 50 plus 60, so 410. What is a combination that satisfy this load using generator having this cost? Okay, and the result is that one. Yeah, generate at its full capacity, same. So yeah, maximum is 90. So 90. And then second chip is 285, and the rest of that is supplied by generator A. Then what you need to do next? Check the power flow. Right? So inject this much power. Actually, that minus 50 is injected. 90 megawatt is injected. Sorry, 30 megawatt is injected, that minus that. Okay. And then see how power flows. Okay, using the splitting and using the superposition, we can determine the power flows here, here, here. And the result is what? Actually, it violates the constraints, this constraint. So you need to adjust the power generation here, here, and there. Okay, so given this, delta P1, delta P2, delta P3, or if you don't want to use delta, just P1, P2, P3, inject, and see how that affects the power flow on each line. And for each line, you need to satisfy the maximum constraints. Okay, so three variables and 3 inequality constraints, and also the P1 plus P2 plus P3 should be 0, right? Because we change the solution from economic dispatch. So net injected power should be 0. Am I correct? 지훈?
베리어블이 왜 3개인가요?
Good question. So yeah, the solution will be how much we need to inject here and here and there. So delta P1, delta P2, delta P3. Okay. Actually, generator B is at its maximum, so delta P1 is generated from here. So it can be plus or it can be minus. So delta P1, delta P2, delta P3. Okay. And describe the power flows using delta P1, delta P2, delta P3 here, here, here. Check. They satisfy the constraints. And delta P1 plus delta P2 plus delta P3 is 0, right? So the result is, yeah. So you obtain, by the way, so when you obtain, what you need to do? Delta P1, okay, so one thing is missing. What is missing from my statement? Reactance is already, you should already consider that when delta P1 is injected, it is splitted like that, considering the reactance. When delta P2 is injected here, it is splitting like this, considering the reactance. You don't know what I'm saying. What are you talking about, professor? 표정들이 다들 왜 이렇지? So you look skeptical.
지금 하려는 게 뭔지를 얘기 못했습니다.
So what, okay. I'm helping you to do your homework. So what you need to do is, when things change it, this one, the maximum capacity is reduced from 130 to 65 because of line maintenance, for example, and generator C lowered its speed from 14 to 3. Okay, so two things have changed, and then the system operator needs to solve it again. So that's your job. So system operator needs to determine how much to increase or decrease, how much to increase, decrease, how much to increase or decrease. Okay? So delta P1, delta P2, delta P3, and delta P1 plus delta P2 plus delta P3 should be 0. So from economic dispatch, we check the line constraints and want to determine this delta P1, delta P2, delta P3. And using superposition principle, check the constraint here, here, here. And what else? And actually, here, here, there, you also need to have the generator's constraint. Minimum generation and maximum generation, right? So here, currently, the 35. So 35 plus delta P1 should be greater than or equal to 0, and the maximum capacity is 140. And here, currently 90. 90 plus delta P2. The maximum is 90. There, Yeah, just the delta P3 is from 0 to maximum. What is the maximum capacity? This one? 85, something like that. Okay, the generator limit and the transmission line limit, they are your constraints. What is your objective function? The additional cost should be minimized. Okay. So your objective function is marginal cost 7.5. 7.5 times delta P1 plus 3 times delta P2 plus 10. Yeah. Times delta P3. So minimize this subject to this. Okay? Still skeptical.
저거는 B가 무조건 다 풀로 제거한다는 가정하에 일어나는데.
Okay, good point. Good point. So if you want to make it general, actually the at the solution, intuitively we know that this generator will produce at its maximum. That is not, that is assumed. Actually, that's the fact. But if you are not happy with that, then delta PB, you need to set that. And variable, we have one more variable and more constraints, right? But the solution will be delta PB will be 0. If you include this one, then you need to modify that one too. Okay, good question. Any other questions? So you know what you need to do now. Okay. So I know it's not simple, but anyway, so after solving this one, you obtained delta P1, delta P2, and delta P3. What's next job? So homework 1. What is then homework 2? What is your homework then? Ji-hoon? You are today's student. What is your next homework? Yeah, delta pi, or just a new pi, pi 1, pi 2, pi 3. You need to compute nodal price again. Okay? And then you will get this number, that number, and that number. So this is the answer, but the process is not in your textbook. The answer is in your textbook, but the procedure is not in your textbook. So I told you already. Okay? So if it does not work, tell me. I didn't do it on my own. Okay? So yeah, pi 1 same. Pi 2, where is it? It's reduced from 11.25 to 3. Yeah, that's kind of obvious because the marginal cost of generator C is $3. So yeah. And the marginal cost of bus 3 is increased from 10 to 12. Check it. Okay. So what happened is low bid by C, and congestion happens here, and that reduces the price at bus 2 from 11.25 to 3, and increase the price at 3, 10 to 12. So what? no, generator D is happy because LMP is increased. That means the increased revenue of generator D. Okay? Why does it happen? Because of two things. The constraint here and new bid there. Okay? And the benefit is for generator D. Okay. Then, yeah, another homework. Another homework 3. This is interesting one. So generator D finds that he did nothing here. Okay, what has changed is the maximum capacity here and the marginal cost of generator C. He did nothing, but actually the generation we started from here. Yeah. By the way, so previously, it generates 75 megawatt, and new bid and new constraints, and then it's 85 megawatt. So it generates 10 more megawatt hour, but anyway, the price is increased from 10 to 12. Okay, so generator D does nothing. Actually generate 2 megawatt more, but anyway, it increases revenue very much. Okay, so it thanks to generator C and the reduced capacity. So I don't want to say he is evil, but after observing what happened now, he decides to exercise his market power. Why? When this capacity is reduced by half, I can take advantage of that. He decided that. So he takes advantage of the constraint on line 2, 3. And actually, currently it's not easy to explain, but to make this system work, generator D must generate 77.5 megawatt. Okay, so he knows that I'm an important generator in the system, so he placed bid. So he increased his bid. How much? By $20. Okay, and because all the generated power here goes to there, the LMP at this bus is determined by this generator, and because this generator increased his bid to $20, pi 3 is 20. Okay, and okay. Suppose that generator D bids $20. He did that because he knows I'm an important generator. Okay, so he increased his bid. And ISO solved the problem, and this is the consequence. So you need to generate 77.5, 0 here, another generated power. So they are different from the previous one. So generator D knows that from the experience or from the calculation on its own. So he bid this one, this much, and this is the consequence after solving all of this procedure. Okay, so your homework 3 is that when generator D bids $20 per megawatt hour, compute, and see you can obtain this result or not. Okay, so change 1, change 2, change 3. So pi 1, pi 2, pi 3. You know what you need to do now. You sigh. Sigh. You look like sighing. Okay. Any questions? By the way, another interesting one is actually, you will compute that and this is the answer. But the interesting thing here is that, this is negative. Negative nodal price. Why is it? Because we are considering, again, power system economics. Any questions? If you don't have any questions, let me stop here. Because next